Welcome to your Algebra 2, Lesson 3.1, 3.3. We're going to solve linear systems by graphing and graph systems of linear inequalities. So your objectives are to solve systems of linear equations and systems of linear inequalities by graphing. Lots of graphing today. Okay, some important definitions. A system of linear equations, also called a linear system, is a system of linear equations in two variables consist of two equations that can be written in the form ax plus by equals c. That's standard form of the equation of a line, and that would be equation 1. And then dx plus ey equals f for equation 2. And the only reason we have symbols other than the capital A, capital B, capital C is because they don't necessarily need to be the same number. But basically you've got two equations that can be written in standard form of a line. A solution of a system of linear equations in two variables is an ordered pair x, y that satisfies each equation. Solutions correspond to points where the graphs of the equations in a system intersect. So we're going to be graphing and looking for points of intersection. If there is no point of intersection, then there is no solution. In this case, the lines are parallel, and your answer would just simply be no solution. There's no way to satisfy both equations at the same time. If one line graphs on top of another line, then there are infinitely many solutions. In this case, the lines coincide. Okay, you have two different equations for the same line, and so there's infinitely many solutions. Every point on that line is a solution, and there's an infinite number of points on the line, so there are infinitely many solutions. So here's pictures. When there's exactly one solution, the lines intersect. When there's infinitely many solutions, one line graphs right on top of the other, and when there is no solution, you've got parallel lines. Okay, and we will come back to this particular presentation when it's time to do the important definitions for linear inequalities. Let's go to our examples. We're going to graph the linear system and estimate the solution, then check the solution algebraically. Now, we spent a lot of time in Chapter 2 graphing lines, and so I expect you to know how to graph a line and to just be able to say, okay, we're going to graph this line. If you need to be reminded of how to graph, either by finding the x-intercept and y-intercept and leaving the equation in standard form, or if you want to review how to graph by putting the equation in slope-intercept form and then graphing, then I'm going to refer you back to the 2.3 videos for graphing and then the 2.4 videos for transforming a line into slope-intercept form. So if you have trouble following, well, how did they graph the lines, then you may need to go back to the 2.3 video if you're happy with just using the x-intercept and y-intercept, and then a combination of the 2.4 video and the 2.3 video if you want to review how to transform an equation of a line to slope-intercept form and then graph based on slope-intercept form. Now, most of you will probably need to pause the video to actually work out the problem and graph. It's a good review for you. So feel free to pause. Remember, that's one of the beauties of these videos is that you actually can pause me during a lesson, do some work, and then come back to the video lesson. Okay, so for example 1, we're going to graph the linear system. That means just graph each of the two lines separately on the same little piece of graph paper and estimate the solution. Well, the problems we've picked out, you're really not going to have to estimate the solution. You're going to be able to see clearly where the lines cross. Then check the solution algebraically. I'm not necessarily going to make you do that on all your problems, but I do want to go over how to do that just so that you'll know and you can check your answers. Okay, so your solution is going to be to graph both lines on the same coordinate plane. So begin by graphing both equations as shown at the right. So you want to pause your video right now and kind of go through that process just to review it and make sure you get a graph that looks similar to what is shown on here. That would be great. If you have no clue how to graph those lines, I suggest you go back and at least watch the 2.3 video, maybe 2 videos, maybe 2.3 and 2.4. Okay, so everybody should have graphed the lines. When I did it, I found the x-intercepts and y-intercepts of both lines. So for the 4x plus y equals 8 line, I got an x-intercept of 2, 0, and a y-intercept of 0, 8. And then for the 2x minus 3y equals 18 video, I got an x-intercept of 9, 0, and a y-intercept of 0, negative 6. So that's how I graphed the two. Okay? All right. And then from your graph, the lines appear to intersect at 3, negative 4. And so we're going to check algebraically just to make sure that that's correct. So we're going to plug in 3, negative 4 into each equation. So in equation 1, we've got 4x plus y equals 8. So we're going to plug in 3 for x and negative 4 for y. And we want to know if 4 times 3 plus negative 4 does indeed equal 8. 12 minus 4 does equal 8. And so it checks in equation 1. Now you have to check in equation 2. Make sure it works in that equation as well. Because remember, it's a solution to both equations. So 2x minus 3y equals 18. So we're going to have 2 times 3 minus 3 times negative 4. And we want to know if that equals 18. So we get 6 minus negative 12. So minus a negative is the same as adding a positive. So we have 6 plus 12 equals 18. And that does indeed work out. 18 does equal 18. So we get a true statement in equation 1. We get a true statement in equation 2. So we have verified that the solution is 3, negative 4. Now, I'm not going to make you do that every time, but it is a good way to check your work. Okay, let's go on and we will look at examples 2, 3, and 4. Here we go. All right. Now, in this book, they like to have you do some classification of the systems. We're not going to worry about that. We're just going to solve the system. So we've got 4x minus 3y equals 8 and 8x minus 6y equals 16. So just like we did before, we're going to graph the first equation, then we're going to graph the second equation on our graph paper. So go ahead, take a couple of minutes. Sorry about that. Take a couple of minutes and pause the video and graph your lines. Do you have your lines graphed? Okay. Again, the way I did it, since they're in standard form, is I found the two intercepts for each line. So for 4x minus 3y equals 8, I got an x-intercept of 2, 0, and I got a y-intercept of 0, negative 8/3, but I needed to change it to a mixed number in order to be able to understand where that was to graph it, and so that's negative 2 and 2/3. So I plotted those 2 points, 2, 0, and 0, negative 2, 2/3, and I graphed my line. And then I went to my second equation, 8x minus 6y equals 16. I found the x-intercept was 2, 0. And then I found the y-intercept was 0, negative 2 and 2/3. So when I graphed them, they graphed right on top of each other. Well, and if you look, the graphs of the equations are the same line. So each point on the line is a solution. And the system has infinitely many solutions because a line has infinitely many points. Okay, don't worry about the therefore the system is consistent and dependent. That's true, but we're not going to worry about it. Your answer for this problem is infinitely many solutions. Okay, so example 3, we're going to solve the system. We're not going to worry about classification. And so I want you to graph both of the lines on the same graph. So take a minute to do that. Okay? All right, well, the way I graph the lines, again, because they're in standard form, I just went ahead and found the x-intercept and the y-intercept. The x-intercept for 2x plus y equals 4 is 2, 0. And the y-intercept was 0, 4. So I plotted 2, 0 and 0, 4, and that gave me the first line. And then I went and I worked with 2x plus y equals 1. And for 2x plus y equals 1, the x-intercept is x equals, or the point where x equals 1/2 and y equals 0, so 1/2, 0. And then the y-intercept is the point 0, 1. So I plotted 1/2, 0, and then 0, 1, and drew the line through that. And I looked and I had parallel lines. Well, they're parallel lines and they're in the same plane. They have no point of intersection, so the system has no solution. Okay, don't worry about the fact that this system is inconsistent. We're not going to focus on that. We're going to focus on the fact that there is no solution. There is no ordered pair XY that satisfies both of these equations at the same time. Just can't be done. All right, let's look at example 4. You ride an express bus from the center of a town to your street. You have 2 payment options. Option A is to buy a monthly pass and pay $1 per ride. Option B is to pay $2.50 per ride. A monthly pass costs $30. After how many rides will the total cost of the 2 options be the same? Okay, so if we draw lines to represent both of these, where does that line intersect? All right, and we've got choices of 12 rides, 20 rides, 24 rides, and 28 rides. All right, so one way to come about this solution is to write equations for each of the options. So for option A, the total cost is going to be the cost per ride times the number of rides. You've got to pay $1 every time you ride, plus the monthly fee because you had to pay $30 to begin with. So that's going to be Y being total cost equals 1 for the $1 per ride times X for the number of rides plus 30 because you have to pay $30 for that monthly fee, so you have to count that. Option B, you don't pay a fee up front, you just pay $2.50 a ride. So the total cost is just going to be that cost per ride times the number of rides because there's no monthly pass, there's nothing to purchase ahead of time. So it's just Y equals 2.5 times X. All right. So to solve the system, you're going to graph the equations Y equals X plus 30 and Y equals 2.5 times X as shown on the right. So when I scaled my axes that I had there, I went by 10s across the bottom just like they did on the slide, and then I did 20s but then marked off where the 10s were on the vertical, okay, for the total cost. And so these were in slope-intercept form. So for Y equals X plus 30, I just found the 30 on the Y-axis. And I could have gone up 1 over 1, but it's hard to see the 1s on there. So as long as you go the same number of units over as you do up, you're good. So I went up 10 over 10, up 10 over 10, up 10 over 10 a couple of times, and plotted points and drew in the ray because you're not going to do a negative number of rides, so you don't need to extend this line to the other side of the y-axis. Okay, and then the other one is Y equals 2.5x, so the y-intercept is at 0, 0, because there's not plus anything, so it's the same thing as having a plus 0. So I plotted 0, 0, and then I could have done the 2.5 thing for the slope, but that's kind of hard, so what I did was I plugged in 10 for x and got that when x is 10, y is 25, and then I plugged in 20 for x and got that when x is 20, y is 50, and I drew my line, and I noticed at that point that 20, 50 was where the point of intersection was. So when you have 20 rides, when you take 20 rides, both plans cost $50. So if you want to double check that, go ahead and plug in 50 into both of them. So for y equals x plus 30, the question is, does 50 equal 20 plus 30? Well, yeah, 20 does equal 50. I think I said that backwards. 50 does equal 20 plus 30. So you plug in 20 for x, 50 for y, and see if you get a true statement. You do. You get 50 equals 50. For y equals 2.5 times x, you plug in 20 for x, and you get 2.5 times 20, and that is 50. So you end up with a true statement there. So 20, 50 is the point of intersection, so 20 would be the number of rides. Oops. So notice that you need to graph the equations only in the first quadrant because only non-negative values of x and y make sense in this situation. You're not going to write a negative number of bus rides. Nobody's giving you any money back. You're paying money to ride. The lines appear to intersect at about the point 20, 50. And again, you can check algebraically. 50 does equal 20 plus 30. And 50 does equal 2.5 times 20. And so the total costs are equal after 20 rides. Okay, that's it for video 1. We will talk about linear inequalities in video 2.